All right, so now we're going to talk about the traveling salesman problem. And the point of the traveling salesman problem is to illustrate what's called combinatorial explosion, which is that as the number of things that you have to combine increases, uh, the number of possible paths explodes, which again we'll talk about in a second. So the traveling salesman problem is this: a salesman needs to travel to 5 cities as efficiently as possible, right? So in this example, the cities are the objects that are to be manipulated according to the operators, in this case, the directions. The goal state is to visit all 5 cities while minimizing the number of miles traveled. And the traveling salesman problem is known as an NP hard problem, which means that there's no known algorithm that could solve it for all cases. However, when the search space is small, it's totally possible to search through the full space, which in this case, with just 5 cities, we can do. And so here is the the search space for this problem, right? So here you start it. It doesn't really matter where you start. You can start at A, B, C, D, or E, but let's just say we start at A, right? And then you could go to B, you could go to C, you could go to D, and you could go to E. And then if you went to B, you could go to C, D, or E, right? If you go to C, you could go to D or E. And if you go to D, then you could go to E and then back to A. And then if you went to E, you could go to D and then to A, right? So these are all the possible routes that you can take in this example. And as you can see, that just with 5 cities, there are 24 possible paths that you can search through. And as a result, searching the space won't be a particularly efficient method for this example, or it just won't be a very particularly efficient method when you have what's called combinatorial explosion. So in solving the problem, right, one could exhaustively search through the space to find the best solution. This is known as the brute force algorithm that the search space takes. However, the space grows, right? The possible number of paths that you can take grows exceptionally fast, and it would take a really long time, uh, even for computers, to search through all the space. So to illustrate this, here's a graph that shows the number of possible paths as a function of the number of cities in the problem. It's hard to see, but with just 6 cities, there would be 120 paths. And with 7 cities, there would be 720 paths. And with only 10 cities, it goes up to around to 360,000 paths, right? So if you recall, the ideal game or problem that Newell and Simon wanted to solve was chess, which is far more complex. So for most cases, the solution space, an exhaustive search of the solution space, is impossible or not feasible for many problems. So, for example, with the traveling salesman problem, the number of possible paths is equal to the factorial of number of cities minus one. In chess, the average number of possible moves is 35, and the average number of turns is 40 per person, so 80. So there's 35 to the 80 possible moves that you can take for chess. And for the Chinese game Go, the average number of possible moves is 200. The average number of turns per person is 125. So that's 200 to the 250 possible paths, right? And so to give you an idea of the scale of these numbers, there are 10 to the 80 elementary particles in the visible universe, and there have been 10 to the 26 nanoseconds since the Big Bang, and there are 10 to the 15 neural connections in the brain, right? So just to show you that there is a large number of paths that you can take. In the next video, I'll talk about algorithms and heuristics.